central limit theorem. This is what we talked about yesterday. 248. Your central limit theorem describes the relationship between the sampling distribution of sample means and the population that the sample means are taken from. Okay, and this is why Gunnar got tired of using the word sampling distribution yesterday. I put this in here, the inferential statistics. This is why we do this. Sometimes it's impossible to get a population, so we have to do sampling. Rather than take one random item, one random sample, and we're not sure if that is a good representation of our population, we do multiple samples. So that, and this is the important part, the reason we do this is that from there, you can make an inference about your population and pretty much be on target if you have enough sampling. And the other day, yesterday, I mentioned that 30 was one of the cutoffs. Some books use 40, and some books use 20. Most of them will say 30. A lot of them do say 40, though. If the sample size n, where n is greater than or equal to 30, are drawn from a population, here's your population mean, here's your population standard deviation, then the sampling distribution of sample means approximates a normal distribution. In other words, as we have at least 30 or more in our sample, and we use those sampling, the different samples, and we take the mean of those samples, we'll eventually make a normal curve, even if your original situation doesn't have a normal curve. Now, if you're interested, and Alyssa went to Khan Academy, I showed it to the other class. I forgot to show it to you guys yesterday. He did this thing where he rolls a dice, and the probability of 1 is there, 2 doesn't show up, 3 and 4 are the same, no 5, and a 6. And as he does this, he puts a sample size of 4. So he takes 4 rolls. He takes the average. Then he does a sample size of 20. He does 20 rolls of this and takes the average. As he's using the means, the sampling means, he actually approximates a normal curve. So we can use this theorem to help us approximate a normal curve in a situation that isn't normal. Now, as we get into this, that's one of the things we check for. Do we hit 30 or more? We look for 30 or more because then we're sure that we can approximate a normal curve. If the population itself is originally normally distributed, then we know any size for our sample will be normally distributed. So 30 is our cutoff to make sure our sampling distribution is a normal curve. And if our population that we took this from is normally distributed, then of course our samples are normally distributed. Okay. And what Gunnar said before, the mean of the sampling means distribution is equal to the mean of the population. This is important. And Alyssa again showed us that they'll reach a normal curve, and the more we have, the greater the curve. Actually, the more consistent the curve in there. So we're going to see why we use this. The standard deviation is the one thing that will change. And what's going to change is this right here. We're going to divide your standard deviation by the square root of how many are in your sample. As the sample gets larger and larger, then you reach closer to the actual population. But for us, what it'll do is kind of move our curve in closer to the mean. So we'll call this the standard error of the mean. We're just a little bit closer to the mean. Instead of being a curve that is spread out like this, we're going to be a curve that goes like this. It pulls us in a little tighter. We want to pull the reins in on our samples. We want to make sure that we're within what we need to be. So let's take a look at how we use this. Once we use this, you're going to say, oh, that's all there was? But I needed you to understand why we do this. So we're on example 2. And I'm on page 249. Phone bills for residents of a city have a mean of $64 and a standard deviation of 9. So this is your whole population of the phone bills for the resident of this city. So they have a mean of 64 and they have a standard deviation of 9. Now, here's where you identify what you're doing. Random samples of size of 36 phone bills, God bless you, are drawn from this population. I have a big city like Newburgh. Can I check every person's phone bill in the city? Is that feasible to look at every person's phone bill? No. So from this city, I'm going to randomly sample size 36 of samples from my city of Newburgh. And this is my end, right here. And the mean of each of these samples is determined. Find the mean and the standard error of the mean of this sampling distribution. Now we know one thing automatically. The mean of the population is the mean of the sample. So therefore, what's the mean for our sample? The mean of the population is the mean of the sample. The samples. 64. They're the same. Now, here's where your big difference comes in. Your standard deviation for your sample, is your standard deviation over the square root of n. All we're doing is tightening that standard deviation up a little bit. So we're going to take your standard deviation of your population, and we're going to divide by the square root of how many is in the sample. This is the whole central limit theorem. It says, give me a little bit tighter on that standard deviation. So you're going to do 9 divided by 6, and you're going to get 1.5. Where before this was a 9, look what we did to your standard deviation. What does that do to your curve, your normal curve? It does what? Shrinks it. It pulls it in tighter. It pulls it in a little tighter. Okay? Now, if you kind of look at the picture on page 249, you see how it's centered around the 64? See where it's centered around the 64? It just pulled it in tighter. It said, here was your 64 before, and it went out 9, all the way out. Now, my curve is going to be centered around 64, but it's going to be like this, narrow, little tighter in here. So look where all my percents are. All my percents are a little closer together. We have to have a way to use our samples and be sure that we're getting the right results. Because from these samples, I'm going to make an inference about the phone bills in Newburgh. I'm going to say, based on all my sample information, I'm going to say the average phone bill is about $64 with a standard deviation of 1.5. And I can come out and say 95% of the people spend X amount on phone bills. Remember, this book is like 10 years old. So $64 is probably not the normal anymore. So this is what we're doing when we use your central limit theorem. We're taking multiple samples, we're taking their means, and we're taking the mean of all the samples. The mean of all the samples should be the same as your population. All right, you guys try this next one. Okay, so your mean for this one would be what? What would be your sample mean? 64. And your standard deviation is going to be your standard deviation divided by the square root of n. So it's 9 over what? 10. Square root of 100 is 10. So look what it did to your standard deviation. It made it even smaller. The larger you go, the smaller that standard deviation. Makes sense, right? If you divide by a larger number, you get a smaller number, right? So as we get more in our sample, we pull this in even tighter, so that now we become a little bit more confident with whatever decisions we make about the samples, that it will be a good reflection on your population. Okay. It's all about us being able to make some inferences about your population based on the samples we get, because we can't go to everybody, like for phone bills. We can't go to everybody in the city of Newburgh, but if we do samples and we check those means and those standard deviations, we can make inferences about our populations. Okay? Not bad. I mean, you'll recognize it right away as soon as you see the samples being drawn. Then you know you've got sampling. As soon as you see samples of X amount, of N amount, whatever they say, 100, 36, 25, then you know that you have your central limit theorem. You're doing your samples.
So that 0.9 was standard error?
Standard error of the mean. And we call that our sampling standard deviation. Yeah. Let's try another one. The heights of fully grown white oak trees are normally distributed. This tells us our population is normally distributed. And that's good for us because once our population is normally distributed, we know that our samples are going to be normally distributed. They're going to follow your normal curve. So we can use any size now. So it has a population mean of 90 and a standard deviation of 3.5. The most important part, guys, is just pull out your information. If you pull out your information, that's the only pieces you're going to use anyway. Your mean, your standard deviation, and your n. So pull these things out. Now, here's where the key is. Random samples. So now we're doing sampling. Whenever we do your sampling, we've got sampling distributions. We got your central limit theorem. We've got sample size of 4. So n is equal to 4. We're allowed to use a small one on this because we know our population is distributed. And we're going to see that in a little while. As long as you know your standard deviation from your population, you'll be okay. So we want to find the mean for your sample. We know that's the same as your population. So what's your sample mean going to be? 90. Now we want to find your standard deviation.
3.5.
Oh, you found it already? So what did you do?
I mean,
okay.
What's the on top 3.5?
3.5 divided by what?
Square root of 4.
Square root of 4, which is 2. So what's our standard deviation? 1.75. See what it did to your standard deviation? It shrunk it down a little bit. Standard error of the mean. It shrinks it down, pulls it in a little bit tighter. We're still normally distributed. We still have a nice normal curve, but it's a little bit narrower. This is your whole central limit theorem. But you kind of have to understand why we're doing this before we actually do these two little things. So is everybody kind of seeing this? You probably won't see this until we do some of your hypothesis testing. And then when we can make an inference about your population based on your sample, we'll say, this is why. So try it yourself 3. Again, they're normally distributed. Pull out your mean. It's a different mean. It's a different standard deviation. And it's a different sample size. You have a population mean. Always pull out your information. It just makes your life so much easier. And a population standard deviation. You know you're good with this because your original population is normally distributed. If it's not normally distributed and your sample size is not bigger than 30, we just stop. We don't do anything. So we're going to take random samples of 16, and you're going to find the mean and the standard error of the mean. So what's the mean of your samples, of your sample distribution? Okay, the mean is the same. And your standard deviation is what? How'd you find your standard deviation?
0.2 over
Square root of 16, which is 4. So what does this become? 0.05. So look what it did. It shrunk it even further down. Okay, just pulled it in tighter. So instead of our curve being like this, our curve is like this. It just brings it in a little tighter. Good? All right, I'm going to give you some to do in the book. And you can work on it now and a little bit on Monday. These two are related, these two. So once you do 13 through 19.